Today, the topic of discussion is on basic concept of refrigeration and air conditioning, that is module 3, part 2, PEME 601B. Myself, Dr. Suman Das, HOD, Department of Mechanical Engineering, Swami Vivekananda Institute of Science and Technology. So in this video, I will discuss the air refrigeration system, Bell-Coleman refrigerator, COP determination, actual air refrigeration cycle, and also I will explain few numerical. So this is the numerical, that is problem 1. A Carnot refrigerator has working temperature of minus 30 degrees centigrade and 35 degrees centigrade. So the Carnot refrigerator, the working range is minus 30 degree to 35 degrees centigrade. It operates with R12, that is the name of the refrigerant is R12 as a working substance. Calculate the work of isentropic compression, isentropic expansion, refrigeration effect and COP of the cycle per kg of refrigerant. If the actual COP is 80% of the maximum, also calculate the power consumption and heat rejected to the surrounding per ton of refrigeration. Now we come to the solution. First of all, the given data from this problem, that is T1 equals to minus 30 degrees centigrade, T2 is 35 degrees centigrade, that is also given in the problem. Refrigerant is R12, that is R12. COP actual is 0.8 of maximum COP, that is already stated in the problem, that is 80% of the maximum, that is 0.8 into maximum COP, that is the actual COP. So from the table of properties, that is R112, we have follow, that is the reference number. So any reference book or any R12 chart, so we will get all the values of that R2, that is enthalpy, entropy, temperature. Yes. Now S1 equals to S2, that is equals to, this is the chart, this is the value that is we are getting from the chart, that is S1 equals to S2, that is entropy value. S3 equals to S4, that is also the entropy value. H2 equals to, that is enthalpy value. H3 is the enthalpy of the refrigerant. SF1, that is the entropy of fluid at state point 1, is nothing but the entropy of fluid at state point 4. This is the value, kilojoule per kg Kelvin. SG1, that is entropy at the gas at state point 1 equals to entropy of gas at state point 2, state point 4. HF1 equals to HF4, this is also this, and HFG1 equals to HFG. So all these values are from the property chart of R112. Now we know that the S1 equals to SF1 plus X1, that is X1 is the dryness fraction at state point 1, SG1 minus SF1. So this is the common formula. We just put all the values and we are getting the value of, so this is the that is 0.6839. Now x1 equals to, so this one equals to this, so from that this you can easily calculate the value of x1, that is the dryness fraction at state point 1. Similarly, the same formula, if you look this formula, that is entropy and this is the enthalpy, so the formula is just the same, just H1 equals to HF1 minus plus X into HG1 minus HF1. So we put the value of F1, HF1 and we put all the values and we can easily calculate the value of H1. So this is the value of H1. H1 means the enthalpy at state point 1. Similarly, S4, we just calculate the value of S4 just by putting all the values, and this is the value of S4, and finally we are getting the value of, so this is the value of S4 equals to this, and finally we are getting the value of X4, that is in dryness fraction at state point 4. Similarly, H4 equals to nothing but this, the same formula. So now from the, now H4 is now now the value of 62.1. Now H4 is now obtained with the help of this formula. Now work of compression, we know that W12 122, that is the compressor part. So H2 minus H1, that is the enthalpy difference. We just put the enthalpy difference of, put the value of the two enthalpies, and we are getting the value of the W12. So W12 is nothing but the work of compression. Similarly, work of expansion W34, so that is the H3 minus H4. So put the enthalpy difference of the two, and we are getting the value of, so that is the work of expansion W34. And refrigerating effect, we know that Q41, that is 4 to 1. So that is the enthalpy difference of 1 minus H1 minus H4. H1 is the higher enthalpy, H4 is the lower enthalpy, that is the refrigerating effect. So we put these two values of the enthalpies, and we are getting the refrigerating effect, that is Q41. Now heat rejected, that is Q23, that is H2 minus H3, that is enthalpy of the two. So just put the value of the two enthalpy, and finally we are getting, that is 132 kilojoule per kg. And net work, obviously W12 minus W34, that is the difference of the two network to work. So we are getting the value of this. Now COP of cooling, so we know that refrigerating effect by network. So this is the refrigerating effect 104, and this is the network, that is 28. So we are getting the value of the COP of cooling. Now in the another way, we can easily write the value T1. So COP is nothing but T1 by T2 minus T1. We just put the value of T1. So this is the value of T1, because the minus 30 degrees centigrade. There are two temperature ranges. One is minus 30 degrees centigrade, and another one is 35 degree. So T1 is this, and T2 is this. So finally we are getting, so this is 3.738. That is the value of COP of cooling. Now the actual COP is nothing but, so that is the COP actual is the 80% of the maximum COP. So actual COP should be 0.8 into 3.378. So finally we are getting 2.99. That is the actual COP. Now the power consumption per ton of refrigeration, that is 3.515. That is the, in terms of ton of refrigeration, that is 1 ton is nothing but this kilowatt, and divided by COP, actual COP. So we will get the value of 1.1761 kilowatt. That is the power consumption per ton of refrigeration. And heat rejected per ton of refrigeration of the to the surrounding is nothing but, that is the 3.5167 plus 1.172. So this is the heat rejection per to the surrounding. So sum of the two, that is the one is the power consumption for, and another is the, so 3.5167 plus 1.176. So sum of the two. Now gas as a refrigerant in reverse Carnot cycle. So if you see the diagram, so yes, so this is the gas as refrigerant in a reverse Carnot cycle. So figure in the PV and TS diagram of reverse Carnot cycle. So this is the PV pressure volume diagram, and this is the TS diagram. So 1 to 2, 2 to 3, 3 to 4, and 4 to 1. So 1 to 2, that is isentropic compression. 1 to 2, that is isentropic compression. So during this process, the pressure increases from P1 to P2. If you see the diagram, pressure increases from P1 to P2, and 1 to 2 is the process, pressure increases, and also the temperature is also increasing from T1 to T2. And volume also, and the volume decreases. So if we increase the pressure, obviously the volume will be decreased from, this is the V1 and this is the V2. So volume will be decreased. Heat transfer is zero, because this is a isentropic process, that means reversible adiabatic process. So there is no transfer of heat. Temperature of the gas increases from T1 to T2. Temperature of gas increases from T1 to T2. So T1 this is, and this is T2, T1 to T2. Work done per kg of gas. So W12 is nothing but, we know that is the isentropic compression. So this is the formula of work done. So P2 V2 minus P1 V1 by gamma minus 1. So we just put the value. So we are getting this. Now next process is process 2 to 3, that is isentropic compression, and that is process 2 to 3, that is isothermal that is isothermal compression. So 2 to 3, so this is 2 to 3, here temperature is constant. So during process the pressure increases from P2 to P3. During the process pressure increases and the volume also decrease. So the volume also decrease. So if you see the volume, and this is V2 and this is V3, so volume will be decreased. The temperature remain constant. Here the temperature remain constant. So here the temperature remain constant. So 2 to 3. So from the TS diagram it is clear that temperature is only T2. Now this is the diagram. So this is reverse Carnot cycle gas refrigerant PP diagram. This is the PP diagram and this is the TS diagram. Okay. Now the work done per kg of gas, so that is in the case of 2 to 3, P2 V2 ln V2 by V3. So this is the formula of work done 2 to 3 process. So heat rejected. So here the Q23 equals to W23 for a perfect gas. So in the case of expansion process, so in the process 3-4, that is isentropic expansion. So pressure decreases from P3 to P4, volume increases from V3 to V4, and temperature decreases from T2 equals to T3 to T4 equals to T1. So, and this is the work done. Okay. So similarly, process 4-1, that is the isothermal expansion. So in that case, isothermal expansion, the work done W41, that is P. This is the formula PV, that is P4 V4 ln V1 by V2, that is RT1 ln V1 by V4. Similarly, refrigerating effect, all of we know that refrigerating effect is nothing but Q41. So that is the work done W41 for perfect gas. So net work of the cycle W net equals to W23, that is W4 minus 1, and that is the W41. So ultimately we are getting the network. This is the network done. Now refrigerating effect. So Q41 is at T1 ln V1 by V4. For isentropic process 1, 2 and 3, 4, so this is the relationship of temperature and pressure. So finally we are getting this because pressure, and this is the pressure P2 equals to P3 and P1 equals to P4. So from that relationship, and this is the T2 and temperature and volume relationship of isentropic process of 1 and 2. So we can write this. So and this R is nothing but that is the compression ratio of isentropic process. So already I have explained that P2 by P1 equals to P3 by P4, that is the compression ratio. Similarly V1 by V2 equals to P4 by P3 here. So we can just equal this P2 V2 equals to P3 V3 and P4 V4 equals to P1 V1. Okay. Now finally we are getting the COP of cooling is nothing but Q41 by W net. So putting the value of Q41 and W net is the net work done, and finally we are getting this, and this is in terms of compression ratio. Thus the COP is a function of compression ratio only. So this is the function of compression ratio. COP is the function of compression ratio. Now limitation of reverse Carnot cycle. So the limitation of reverse Carnot cycle, number one, that the isentropic compression and expansion process require high speed, while the isothermal condensation and evaporation process requires an extremely low speed. So this is the first limitation. This variation in speed of air of a cycle is not practicable. Similarly, number two, it is difficult to design an expander to handle a mixture of largely liquid and partially vapor. So that type of expander is to design is quite tough. Number three, because of the internal reversibility in the compressor and the expander, the actual COP of the reverse Carnot cycle is very low. Number 4, with gas as a refrigerant, it is not possible to uh, devise to in practice isothermal process for heat absorption and rejection. And number 5, the stoke volume of a gas cycle cylinder is very larger, resulting in the poor actual safety. Now the Bell-Coleman or reversed Breton cycle, that is also called the Joule cycle. Joule cycle. So Bell-Coleman cycle, reverse Breton cycle, or Joule cycle, these three are same. The Bell-Coleman cycle was developed in Bell-Coleman in the light food by the reversing the Joule's or Breton cycle. The schematic diagram of such cycle. So first of all, I just show that is the process, and this is the schematic diagram. It is the Bell-Coleman or Joule cycle. There are four processes. 1 to 2 process. So this is 1 to 2. It is clear that that is the isentropic compression. Similarly, process 2 to 3, that is constant pressure cooling. 2 to 3, that is the constant pressure process. So in that case, the heat rejected, pressure is constant. Heat rejected Q to 3 is nothing but Cp into T2 minus T3, T2 minus T3. So if we see the diagram from here to here, that is 1 to 2, that is isentropic compression. So the volume will be decreased and the temperature will increase. So here the temperature increases. 2 to 3, that is the expansion. 2 to 3, that is the expansion. The pressure, the constant pressure process. So due to expansion, the temperature will fall. So 2 to 3. So 3, the temperature will fall. Again 3 to 4, that is the expansion, and that is the due to the expansion. So the volume will increase, and 3 to 4, the temperature again fall, and 4 to 1, 4 to 1. So this is the constant pressure process. The volume will expand. So and this is the 4 to 1. So that temperature will again rise. Now the process 3-4, that is isentropic compression, isentropic expansion process, already I mentioned, and process 4-1, the constant pressure and the constant pressure expansion process, that is 4-1, constant pressure, that is the expansion process. The cold air from the expander is passed to the refrigerator, where it is expanded at constant pressure, that is P4 equals to P1, P4 equals to P1. The temperature of air increases from T4 to T1, and specific volume increases from V4 to V1. So specific volume, that is V4, that is V1. So there are four processes: 1 to 2, 2 to 3, 3 to 4, and 4 to 1. So this is the schematic diagram of Bell-Coleman air refrigeration cycle. So that is 4 to 1, that is the refrigeration part, and 1 to, that is 1 through the after compression, that is the compressed refrigerant entering into the, this is the chamber, this is the cooler, that is through and due to cooling. So after cooling, that refrigerant is entering into the expander for the expansion. After expansion, it is entering into the refrigerator. So this is a cyclic process. So this is the diagram: 1 to 2, 2 to 3, 3 to 4, and 4 to 1. So this is the isentropic compression, the constant pressure heat addition, and this is the constant pressure heat rejection, and 3 to 4, that is isentropic expansion, and 4 to 1, that is the constant pressure heat addition. So this is a cyclic process, and this is a PV diagram, and this one is the TS diagram. Now in this case, the work done during the cycle per kg of, that is work done, that is W is nothing but the heat rejected minus heat absorbed. So Q23 minus Q41. So that is the total amount of heat rejected. So coefficient of performance, COP, is nothing but heat absorbed by work done. So we just put the formula value of that. Q41 is Q41, and this is W, and ultimately we are getting, it is 1 by T3 by T4 minus 1. So that is the coefficient of performance. So for the isentropic compression, so we know the relationship between temperature and pressure. This is the temperature and pressure, and the isentropic expansion, that is the relation between temperature and pressure. So here P2 equals to P3 and P1 equals to P4. So from the relationship we are getting this value. So ultimately T4 T3 by T4 is nothing but the in terms of pressure ratio. So Rp to the power gamma minus 1 by 1. And finally, there is a pressure ratio already I mentioned. So COP is nothing but 1 by Rp to the power gamma minus 1 by gamma. So COP is the in terms of pressure ratio. Okay. Thank you. Thank you very much.